Okay, before the break, we were looking at some, finishing up that stuff about animations we ran out of time for last week. The next thing is another one on the list of major learning objectives, and kind of like vectors, back to the same thing. It's on the list of major learning objectives for the course, and I had a lot of trouble finding a viable resource. Like, there's no shortage. Next up is physics, and just like vectors, there's no shortage of resources on them, but they're set up even at the introduction level for what the normal introduction level would be, which is usually a higher class than this. Vectors usually first show up in a trigonometry class, and in the simplified version of Physics 1, trigonometry is a prerequisite. But those are not prerequisites for this class. And really, like, goes back to the name, right? Simulation and game development.
Are you going to make them prereqs?
What's that?
Are you going to make them prereqs in the future?
Probably not.
Okay.
Because that'd be a lot of high level math. And just like vectors, we don't need to know everything about physics. If you're heading in, if you're very, during all time constraints for a game development course, we just need to see some basic points. Enough to debug when we need to debug things. If things are not behaving correctly, we just want to get some basic ideas of Newtonian physics. We don't need to know everything about Physics 1. If you're very serious about game development, you probably want to take a Physics 1 class at some point and study Newtonian physics in depth and understand what's and develop an understanding of what's going on. But we just want to give our games a touch of realism or simulations if an engineer's going to pay us to make a simulation for their new product, which uses the same skill as developing a game and pays a whole lot more, or pays a whole lot more consistently. Right? Game development, it's that's an art form, hit or miss whether people are going to buy your game or pirate the game. If it's for money, you know both are going to happen, but it's hit. We can't guarantee in advance how much it's going to be, but when you go and make simulations for engineers, you're going to get an hourly paycheck, or probably a monthly contract fee, and it just gets broken down like an hourly paycheck, but a more reliable paycheck for the same skill set. And in general, we probably jump back and forth between them and not do either one, because one of them will do. One of them comes with a reliable paycheck that isn't the most interesting work, and game development, the paycheck can be hit or miss. So a nice mix of both is a great way to apply the skill set. Yeah, part time, and then in your free time, develop games and hope that pays off like a lottery ticket later. There's different ways, but we will want a touch of realism to it. And in order to do this, we often want to follow the laws of physics. When we don't, like when our game gets overly cartoonish and we have those ridiculous things happening, it's going to be obvious, and then we're making up the laws of physics. So we have ridiculous things happening, but they're going to still be within reason for the laws of physics we developed for our overly cartoonish scenario. Like Bugs Bunny and Daffy Duck, right? Whenever a bomb would go off, Bugs Bunny was always far enough away that he didn't get turned black because of the bomb going off. Right? There's still the laws. It's not non-realistic laws of physics, but there's still laws of physics so that Bugs Bunny didn't get hurt.
As long as they're consistent, any laws of physics are reasonably reasonable, as long as a person can understand what they do is always going to result in the same thing.
Yes.
Like it's that whole suspension of disbelief. They're like, okay, this is how this world works. All right, as long as it keeps working the same way, their chances are, if somebody's already invested in it,
that's exactly what it is.
They're gonna go with it.
The predictability. So we need to, and sometimes our prediction doesn't exactly match up. And in particular, how we control things. So I've already mentioned the car control. We have two controls on how we change where the car is located at, as far as speed. skipping the turning one for now. We have a similar thing in games. But as far as speed, how quickly we move between where it's located. In a car, we don't just change the speed immediately. We don't just teleport. We don't end up in a different spot. We don't have a steady speed between them. What we do is we control how quickly the speed of the car is changing. It's either getting faster quicker or it's getting slower quicker, one or the other. And we want to control our games the same way. So everything's going to have a position. As a position, that's our starting point. Back to like the math class axes. It's got some position, and then a change in position is a velocity. Change in position is velocity. I'll write it that way so I don't run out of room. I'm going to write it in math notation as well. Change in velocity is an acceleration. So we need to go through that process if we want something to move. Just like with our car. If we want our car to go forward, we change the acceleration up. If we want our car to stop, we change the acceleration. Because a brake, a negative acceleration, slows our car down, and that's how we get it to stop moving. But we change the velocity, and then the velocity changes the position. So that's how we get from one spot to another. As some sort of a vector, what I do there, 2 over, 1 up. That's what I was trying to do. So 2 units over, 1 unit up would be a move, equivalent move. Or in the other direction, negative 2 units over, negative 1 unit down. Negative just goes the opposite direction. So back to that. Vectors have a magnitude and direction. All of these things are going to, anytime we deal with these, position, velocity, and acceleration. So position, I'm going to use this notation today. X, even though we're talking about like X, Y coordinates, write X to abbreviate that. And that is a vector. Right, the original little dot I drew here was 3 units over and 2 units up. So instead of just that point in space, we can think about it being that distance from the origin. The way I said to think about vectors the other day. The arrow that goes from the origin to that point. That's how we want to describe it. So it's an X with a little arrow over it. Velocity, the movement that the player is going to think about, right? Back to driving a car. When you get on the interstate, you're thinking about your speed, right? Going on the interstate, thinking about, okay, go 70 miles an hour, or whatever the speed limit is through Indiana. So you're thinking about 70 miles an hour, and then you adjust your acceleration, either more acceleration positive to go faster, or negative acceleration to go slower, and just keep balancing back to that velocity to the change of position you want. And that definition I wrote, the change of position. So we'll typically see that written as a V with a little arrow above it because it's a vector again. 2 dimensions, 3 dimensions, however many we're working in. There's going to be multiple components to a velocity. And that is a change in position. So this symbol here, the capital Greek letter delta, that means change. So, or it is a different color, maybe a little red note to the side here. Delta is defined to be change. End minus beginning. That's always our formula for it. The ending value minus our starting value. So a change in position but a change in position doesn't happen instantly, right? So it is with respect to time. I write the t in that way because we'll often see it written that way, but t is like our variable. So change in position is going to be whatever our x value is. I'll write little subscripts x2 minus x1, or that way, divided by t2 minus t1. I'll draw simple ones there. So our ending position at the ending time, so we move 5 miles in 8 minutes time, how fast are we going? 5 miles in 8 minutes time, we could just divide that out, punch in the calculator, get some small number, right? Of so many miles per minute. Or 8 minutes is what, about 1/8 of an hour. 0.625, yeah. But at that point, the computer's going to do the calculation for us. Right? The programming, we just need to be aware of setting up the formulas. So velocity, which again is, I'll go ahead and write this otherwise. These are all going to be functions of time. Time is our variable, and our time is our independent variable. If you remember from math class, basically it's going to look like this. Time, that looks like a mess. Time is what's on our x-axis. The horizontal axis is always going to be time change when we think about these things. The next one, acceleration. Use an A for that. Acceleration is a change in velocity. So again, the change in the velocity as a function of time, which I'll do V2 minus V1 again, just for consistency. T2 minus T1. This we can plug all these in, but the car might be a good example. If we go slow down from 50 miles an hour, getting off the interstate, slow down from 50 miles an hour to a stop, full stop. So we slow down by 50 miles, by a velocity of 50 miles per hour in 2 minutes time. We slowed down by 50 or 25 miles per second, right? It changes with time. That's why I was mostly drawing. The big thing I wanted to get up here, what we need to think about here are the units. So I'm going to put these in square brackets. whenever you start hitting problems with your game, what's called dimensional analysis. If we think about the units in the formula we put together, we can check and make sure we're ending up with the right units when things aren't working correctly. So from these formulas, position, I'm just going to put M for meter, whatever our distance one is. I'll go with the System International. The standard was supposed to be the worldwide system. So position measured in meters, but y'all know how many units we have per position. Probably pixels on the screen, but whatever our distance is, when we get to velocity, we're changing that with time, so maybe seconds. So our units are going to be meters per second. And on acceleration, the one that we should actually be controlling in our code, our units are velocity, which we know is meters per second. And then again, we have time on the bottom again, so per second. So meters per second, if we did all the simplification, that comes out to meters per second squared. Is a much easier way to say that. Seconds are squared on the bottom. It doesn't look as messy when we do that. But if we're trying to think things through, it's easy. It's probably easier to think it through this like meters per second, which is what we need to see from this debugging stuff. So when things start acting a little bit wonky and you're not sure why or where you got off in your formulas, first thing you want to check is forget all the numbers, all the variables, all that stuff, and rewrite all the formulas with just your units and make sure you end up with the right units at the end. It's called dimensional analysis. So going down to acceleration, this keeps going if you take physics or calculus. Change in acceleration is a jump, a change in the jump is a jerk, a change in the jerk is a nudge. And there's names going all the way down. They just keep going and going and going. But as programmers developing games, we're mostly going to be worried about acceleration because the acceleration an object has actually dictates how it interacts with other objects. And this is Newtonian physics. Just on screen, yeah. So here, just a handful of formulas to kind of think about and will help you debug whenever things start working, acting funky. Because the game engine knows the laws of physics really, really well. Sometimes things you did not expect might happen, or sometimes you might just want to know how to cause what you want to happen without hard coding it in. Basically, the realistic interaction. So the first one, Newton's first law. Has everybody heard of Newton's three laws? In our society, you've probably heard of it before. The first law: an object in motion stays in motion unless acted on by an outside force. That's a different one. We'll get to that one. But the first one is yeah. And once something is moving, it's going to keep moving until something stops it. Yeah. That's the third one. On the first one, an object in motion stays in motion. That's the one that gave the astronauts a lot of trouble on the moon because they trained in swimming pools because the buoyancy made things lighter, and they were like, okay, this is what the weight's going to feel like when you get on the moon, but it did not change the mass. And if you have a big backpack, if you're moving 200 pounds and try to stop, it doesn't matter how much it weighs. It takes the same amount of effort to stop 200 pounds moving. Anybody seen videos of like the first astronauts doing backflips and stuff on the moon and?
The only problem is there's a lot of extra resistance.
Yes. Yes,
There's larger to stop in water than it is in a vacuum.
so training in water threw off the inertia, they weren't prepared for the inertia. And I've probably seen videos where they go to do something and just fall down. And
Also, the
and
suits also didn't help.
so, yeah, once something is moving, that's important for game development, because if we're making a realistic simulation, once it's moving, it's gonna keep moving. So we have to watch out for that. Newton's second law is a big one for coding. So the second law, force is mass times acceleration. This is, force applied arises from mass and acceleration, would be how that is actually worded. The exact translation from Latin for that. Everything happens because of forces applied. So it's back to the first law. In motion state, something in motion stays in motion unless acted on by an outside force. Everything happens because of the forces applied. The third one, it's also very important for us. That's supposed to be an R. The third,
For every action.
yes, for every, yeah, we want to say this every force, there's an equal opposite force. Every force has equal and opposite. Which mathematically is going to look like force 1 is equal to the negative of, I'll put a little 2 on there. Right, negative just goes in the opposite direction. So every time we do anything, every time our game character graphics, in order to work with the physics engine, we have to give it some sort of mass value. We start moving it, change the acceleration, and that creates a force. Every time we do something with that force, it's going to affect other things in the world as well. Then we just plug in numbers, right? This isn't a math class. Y'all know how to plug numbers in that calculator. What we want to think about is the intuition of what these are doing. So, in particular, word that's going to be important here, let's call this the normal force. That opposite one, I'll draw a little arrow there. That opposite one is called the normal force. And this can sometimes throw off your intuition. The normal force is the one we experience. We don't feel the force itself. We feel the equal and opposite. For example, standing on Earth, gravity is pulling us down towards the center of the Earth, right? But if you're standing on the floor, what do you feel? You feel something under your feet. So you feel the floor pushing back against your weight. You don't feel yourself, you can't feel yourself being pushed into the floor. Hence the name normal force. So that becomes very, very important, because if we code the wrong one, things around us are going to start acting incorrectly as far as our anticipation. So that's a big debugging point. Obviously, these are the 2 biggest ones for debugging points. This is the one we're going to build every time, but we actually want something else out of there. We'll get to it in a moment. And the third law is an important one that will often cause bugs, because we might inadvertently cause the normal force. So we accidentally coded the equal and opposite force, not the force that should be applied to the object we're moving, or we want to move.
So we want to code F2, right?
Yes, probably F1.
Oh, okay, so the
Yeah,
actual.
let me change that. F is the force we want, and I'll put a little N beside it. So the opposite force, the normal force, is equal and opposite to the one we want.
So would those be handled by the physics engines and mechanics?
Yes, but we would have, like, things get applied in the wrong position. So a very quickly drawn car. Which way does force apply in order to make a car move forward?
Backwards.
We experience the normal force, so to make the car move forward, we have to apply a force backwards.
Car tries to shove the road backwards, the road shoves it forwards.
Yes. Yes. So that can get coded wrong sometimes, which will have odd things, because if we applied a forward force to our car, the road's going to apply a backward force to our car. It's going to go in reverse. Or if we apply the forward force to the car, other things that are around there might experience the interaction of that force incorrectly. They all link together.
Well, it depends on what you're ultimately looking for, where you're applying.
Yes. Yes, we're not recreating the universe, so sometimes we take shortcuts and stuff, but remember, we experience the equal and opposite side. The car pushes back on the road, which makes the road push forward on the car, for an example. These things just kind of show up when debugging. So kind of keep those in mind. And then, yeah, Newton's 3 laws. Inertia, if physics are applied, once something's moving, it's going to keep moving. Force is equal to mass times acceleration, but do we have a force pedal in our car? Or a wheel to adjust, a switch to adjust the mass of the car? The thing where we actually control acceleration is equal to force over mass. Sometimes that's a more useful one to think about it in. The force that we apply to that car for its given amount of mass is going to create an acceleration. That acceleration is like when our car accelerates, that's a change in velocity, that changes our position. And that's the one we care about in the game development. I have an example here. So got like maybe some enemy character in the game. Maybe talking a big ogre that has a mass of 3. I just made up a number. So a great big ogre with a mass of 3 charges at it with an acceleration of 0.2 for 12 frames of the game. Plug that in. Mass times acceleration, 3 times 0.2, 6. And our character has, let's say, a mass of 1, a dwarf, so way smaller than an ogre. Produces an equal and opposite force going the other way, which is going to be negative 0.6. So ogre has a mass of 3 and an acceleration of 0.2. So the force he's running forward with is 0.6. Then our little bitty character over here with a mass of 1, when they run into each other, it's going to push back at negative 0.6. Right? Push back with a force of negative 0.6. So those characters collide with each other, and they're going to bounce back. Right? Think of a joust running at full speed. But how far do they bounce back? We can plug it in this way. So we have the force in both cases, and we have the mass. So a force of negative 0.6 for that ogre's mass of 3 is going to give him a backward acceleration, and the force of 0.6 applied to our mass of 1. Oh, maybe our character is standing still. So our character is standing still and this ogre just charges it. I should probably say it that way, otherwise it's going to get a lot more complicated.
So that, I mean, would that make the mass 0? Okay.
That's the numbers I wrote down. So he's charging forward with this acceleration. Here, our acceleration is 0 to start with. So we're standing still. The ogre runs into us. There's that equal and opposite force. The ogre bounces back at 0.6 divided by 0.3, or divided by 3. That's back. He bounces back with the same acceleration he ran forward with, which was obviously easily within running speed. So a speed he can catch, he should be able to catch himself and stop pretty quickly. Our character is going forward at a bunch quicker. It's going to shoot off this direction pretty quick. At 0.6, he's going to shoot off 3 times faster than the ogre ran into it. And well, the ogre was moving forward at 0.2, and then he gets a force backwards of negative 0.2, so those balance out. So really, all he does is stop. But our character goes flying off in the distance. Does that kind of make sense? See how those forces interact with each other? And this happens all the time in games, so we will need that in debugging. Computers will do the calculation, but sometimes it throws off our intuition. So we want to keep an eye on those things. I need to erase this side of the board. Is that okay? There's a slight change to that. There's another part to that coming up in a moment that'll be very, very important. So that's where our intuition starts. It's right from Newton's laws. Before we get to that, negative acceleration or deceleration. How do we slow down when we're done? And that's going to come from friction. So gravity downward is an acceleration, right? If I drop something, so I got this pin here. Right now it has velocity of 0. If I let go, it starts moving. So its velocity is changing.
By the force of gravity.
Yes. So it's an accelerate. It's an acceleration. It goes faster and faster and faster as we start falling down. So it creates a force. The force of gravity is called weight. So weight is independent of mass. It depends on what we're close to. But it pulled into some surface below. I'll do this one with a picture. So I have this box. I'm gonna write a little g for gravity is accelerating that down, which means we have an equal and opposite force pushing back up, right? The floor is pushing back up on it, which that's also a good, that's what we actually need from physics engine. That's what we absolutely have to have. The rest of physics just comes along with us, but that boundary between it, where the equal and opposite forces can happen, the interaction between things. So it pushes back against it, forms a tight seal between the two things, and that's where we get friction. We'll write this F sub G. So the force of gravity or weight pulls it down into the floor. We get a normal force pushing back up, right? That's what we can feel under our feet. We feel the normal force, the equal and opposite to what gravity, to our bodies being pulled down. we're the ones that move, right? Earth doesn't move, so just like the tires pushing backward on the road doesn't move, so the car does. We're the ones that move by gravity, pulls down. We're trying to push on the earth, but the earth's not going to move just from our weight, at least not. The earth's not going to move, so we feel a stop, and we get some sort of seal in between there. So if we have some sort of force going forward, I'll just write that as some sort of forward force pushing on that. There's another one that pushes back. And this one wants to be equal and opposite, but it can't always be equal and opposite. And this is sort of the control we have on slowing down how we stop. We don't want our character to stop moving when we release the button on control. That's going to seem unrealistic to the players. They're going to have trouble predicting things. Just intuition is going to expect the thing to keep moving forward. And if the character just immediately stops as soon as we let go of the button, the forward button, they have to have perfect timing in order to stop at the right spot. Right? But if they control their speed, and then when we let go of the button, it just slowly decelerates to the right spot, it gives some wiggle room for the player to predict what they need to do in order to end at the correct location.
And that also just depends on the game itself too. Because sometimes you do have things where you let go of the button, the character just
Yes. Every game's different, but in general, that is a very bad thing, and that takes more getting used to than even rough wiggle room here. But the friction is what slows us down. So the force of friction is this formula: mu times the normal force, where that Greek letter I put in there is usually some coefficient, some number based on all right, the actual word coefficient based on material. So mu.
Okay, yeah.
The Greek letter mu. It's the coefficient of friction is what it's actually called. Coefficient of static friction. It gets a lot more complicated, but this is based on the material. So like carpet is going to have a very high coefficient there, like maybe 0.9. So my body pressing, weight's pulling me down, whatever our weight is, 200-ish, 250, I don't know what I weigh. I haven't been on a scale in decades. But the weight's pulling me down, the normal force, all right, that is in P and N. The normal force pushing back up is going to be the same as that. So if it's 200 pounds pushing back up. But the carpet's not ice, so it's not perfectly smooth as far as something pushing back. But push forward, some percentage of that carpet prevents me from sliding forward, right? Maybe 0.9 versus on ice, it'd be 0.1. So we barely get anything on ice. Push forward just a little and we're going to slide for a long, long time. So some sort of number based off that. This one we do end up coding because if you don't manually code this at spots in your script, like how much friction is going to push back, we'll see this in an example at some point. If you don't manually code that, you basically have to set every single parameter for all of your models. And you have to set it up for every single object in your game. And it gets really, really, really time consuming versus the 3 or 4 little lines where you're gonna actually need to worry about it. So that one is in the physics engine, but it's something that often gets coded. But just remember there's some value. So like a tile versus carpet. Carpet's going to be really high, so we get almost that entire normal force creating friction, slowing us down. If I try to slide something across the carpet, everything I see has wheels. Can't slide stuff with wheels, but y'all have seen that before, right? Sliding something across the carpet versus sliding something across the tile floor. You push with the same amount of force, and it's going to go further. So eventually, it's going to slow down and stop anyway. But the tile floor has a much smaller scale factor. You can think of it that way. It's a small scale factor that we use to slow the number down, or slow things down. Mostly, we're just looking at words. I guess that's the big thing. Some of the terminology that you will see in game engines, knowing what they are. This one ends up getting coded. These two of Newton's 3 laws show up a lot when we're debugging, because weird things will start happening. We have to track down where they're happening from. One last one about the forces that I want to put in here. I guess there's a little bit of room here. Mostly just remember these words. That's what your quiz this week's going to be about. It's going to have some vocab terms. There might be a question like this, but I probably won't have you punch anything in the calculator. Just remember which equations are which. Friction's fun. It kind of looks like that. That's an easy way to remember that one, that formula. But it's some sort of scalar multiplier that gives us friction. The other thing to worry about, well, we can see it from this situation. Our character is standing still, the one we actually punch numbers into. Some, maybe that's a little dwarf, and some big ogre runs at it and hits it, and we calculated all of that stuff happening at once. But how many things in the world really happen instantaneously? Or in a game engine, because we're talking about game development, nothing really happens instantaneous, right? You're gonna have at least the processing time, but it's probably not gonna, at the very soonest, it's gonna be the next frame of the game. So everything that happens, that's where these Newton's 3 laws fall apart, because nothing happens instantaneously. So a more important factor than force is impulse. And this is where things can really, this is the important one to watch when debugging your games. I'm going to write the formula: force over delta t. So force over change in time, which a change in time, we would probably read that as time interval. Force per time interval. It's a nice way to state that in English. The time interval over which we apply the force. So for example, let me draw a couple cars here. Have this car moving forward with some force, right? It's already got an acceleration. Well, let's say it's moving forward with a velocity. So there's not currently any acceleration, but when we go to stop it, there will be. If this is positive, then there's going to be an acceleration in the negative direction to stop it. 2 ways we could stop that car, or we could hit a brick wall. That'll stop the car, right? bring the car from whatever its velocity is, say 60 miles per hour to zero really, really quick. Or we could hit a row of bushes.
It'll be not as fast.
if any at all. Well, it depends on the game. The Grand Theft Auto is infamous for its concrete bushes.
Well, also, let's think about real life. In real life,
Yes.
this one's going to completely destroy the car.
Probably,
This one might scratch the paint.
like even if it's a little.
But if the car is going 60 miles an hour, it takes the same amount of force to stop it. If that car is moving forward, right, whatever the mass of that car is, it has a certain velocity. So to get that velocity to change to zero is a given acceleration. That doesn't change. The mass doesn't change. So no matter what, to stop this car, we have to apply the same amount of force. But do we apply it by hitting a brick wall or a row of bushes? The difference is the time. The brick wall is very, very quick. And the row of bushes is going to spread that acceleration out over several seconds. That's what impulse is. So the force applied and the time interval that it's applied over. That's a very, very important one for when we're developing games. And when you go and like plug numbers in inspectors in all of your game engines, whatever game engine you're using, you start plugging numbers in and run numbers in your code. You're gonna be thinking about the forces applied, but keep the time interval in mind. You have to think about how the impulse is more important than the force itself. The impulse that force creates is what the player's intuition is going to be based off of, and really determine how easy or hard the controls are in the game. And if your impulse gets off, basically your game will immediately lose all sense of realism. The predictability. Earlier we were talking about we can make cartoonish stuff. We can change the laws of physics a little bit for our game, and people will be able to work with it as long as it's still predictable. But
What's gonna happen? Wacky and weird it gets. If you hit that button, you know what's gonna.
And this is the most important part on that. But again, your quiz is going to be like vocabulary terms and stuff. You will see these things in code. These are keywords used in the libraries. So we're not in a physics class. We're not going to do calculations. So just make sure you're aware of the formal definition of what friction is. Friction is the equal and opposite force that can't quite reach the equal part. It's opposite. It's in the opposite direction. But because of the normal force, you think of it as the tightness on the seal between the box and the floor it's sitting on. How tight is that seal to produce that equal and opposite force from third law? The last one I have in my notes is something that it seems to show up quite often when debugging that. Okay, I've erased this last section. Those laws, you've probably heard those before. The physics quiz is not going to be hard. It's just going to be some vocabulary stuff, maybe a couple of these formulas, what they mean. I'll get that written within the next day or so. It should be either tonight or tomorrow morning. But I didn't want to write it ahead of giving the lecture and figuring out what needs to be in there. Mostly it's for debugging. The computer's going to do all the calculations. We just need to know how to set up the formulas. Conservation is one of the most important things. In that example I just erased with the ogre running into a dwarf, we expect certain things to happen. The two most important properties are gonna be energy and momentum. Momentum is the product of mass and velocity. It's traditionally written with a P because a lot of the other letters were already taken at the time it was written. P is mass times velocity. So that's, yeah, the formulas are what you are going to show up on the quiz as well, because that's something you're writing your code, right? If you want to work with momentum, you're going to think, okay, mass times velocity, you write that in your code. Might need to code it occasionally. It's a property of mass in motion. Mass in motion. We already mentioned inertia, Newton's first law. What happens when mass is in motion?
It stays in motion until something acts upon it.
Yep. It stays in motion, mass in motion stays in motion until something acts on it. But we can't, the motion doesn't just disappear, right? Is this going to show if I'm throwing this marker, right? It's coming up and down and in my hand, but it doesn't suddenly disappear whenever it hits my hand.
It goes into your hand.
My hand has to move in order to absorb the motion that the marker had and start it. Right? If I don't move my hand, the motion goes back into the marker and just in a different direction, right? So you think of it that way, the motion back to inertia, it keeps moving until something acts on it, but the motion doesn't go away, it just goes someplace different. This is the one you were thinking of earlier, energy. We can't add more energy. We can't. We only have a certain amount of energy. It doesn't change. In the same way, so you got characters running into each other like that ogre and dwarf charge thing again, and the ogre runs into your dwarf. The dwarf goes flying like you expect, but the ogre goes flying back to the set at the same speed. Something's wrong, right? You're immediately going to know that they.
Unless that was intentional, something is very wrong.
Yeah, you're going to know the momentum is off. I'm going to write some little subscripts for the conservation. So I'll do like mass 1 is moving at some velocity. I'll call that velocity 1 plus mass 2 times some other velocity. And in the end, the mass doesn't change, right? The ogre runs into the dwarf. They're still the same size as they were before, so that's not changing. We still have mass 1 and mass 2, but their velocities changed. So mass 1, and I'll put a little apostrophe up here. That's traditional notation for it. We would read that as prime. So velocity 1 prime. So it's different than this velocity. We don't know what it is. We don't know what it is in this case, but it changed. And again, I'll put the little apostrophe up there. It's just indicated something different than what it was, but the equal sign in the middle. The ogre's speed should slow down, and the dwarf's speed should increase. So we have different speeds after the collision, but if we add them back together, it should be exactly the same as it was before. So just the conservation thing, the important part is the equal sign. Our velocities will change. The mass obviously doesn't change, but we don't lose anything. It has to go somewhere. in the real world, we get like sound and heat and all sorts of, it gets really, really complicated where it goes. But for game development, we can avoid a lot of the complications because the sound effects are completely separate. But if that gets off, again, it messes with the intuition, kind of like when impulse gets off. It makes it so the player can no longer predict what's going to happen. Energy is the same way. A good intro to energy is maybe work, which is force applied over a distance. So work is some force applied over a distance. So instead of time, this, in this case, just what sort of distance are we applying that at? Distance being a change. Let me write out these formulas more precisely. Force is mass times acceleration. We already saw that. And distance is a change in position. So change in position without time involved. But acceleration is a change in velocity. So mass times a change in velocity times a change in position. This is, we have time on this one. So that's like x2 minus x1 over t2 minus t1. And in this one, we just have a change in position, x2 minus x1. So to kind of work those out, we would average them. I was going to start to derive something, but notice how we have things happening. Mass and velocity, so we have momentum again. Have it spread out over a distance. I had some complicated math. I just realized that that's probably a little bit complicated there. But we're doing something and spreading it out. So it's back to where those intuitions fall out. So energy always applies. I'm going to stop that there. I was going to take that a little bit further, but it'll lead to another formula that was about to get really, really complicated. I should probably put a note in here. Cross out the complicated math in these notes. At some point later, we'd get what was called kinetic energy. I'll spell the word out. The important thing is work is doing something spread out in space. Do a bunch of complicated math, and we get down to kinetic energy, which is 1/2 times our mass times velocity squared. That equation will be very, very important for game development. We have potential energy in the real world. Like if I hold this pen up here, there's potential for it to fall. It has energy, but until I let go, that energy can't do anything but wait. But in game development, once it's moving, then it's kinetic energy. Kinetic just means moving. This formula right here will be very important as far as conserved quantities, because once we're doing stuff in our game, once things are moving, we can't just stop that movement suddenly. This is why games where when you just release the controls and everything stops, take a while to get used to. Especially if you played a lot of those games, not as long. But you have to do some practicing with the controls to get used to it versus other games like Nintendo is really, really good about accurate physics. People just start playing and very quickly pick up on what the friction of the ground is. So when they need to let go of the control for a given speed in order to slow down to and stop at the correct spot.
Oh, instead of like micro movements, you had acceleration was something. No, you said if you move like immediately,
Yeah.
you would have to do micro movements.
Yeah.
Instead of like letting go.
Yeah. If you just stop, you might end up in the wrong spot unless you can teleport to that spot. Because the game's moving fast, you're moving suddenly, and you have to just release the control at the exact right time in order to suddenly stop at that right spot. So that's why we want to recall those things. Let me heard another formula up here earlier. Force, mass times acceleration. I'm going to ask you about a couple of these formulas. This one, we have some sort of object, or in the case of a game, it's going to be graphics, and we kind of make up how it applies to other things, whether it's really heavy, really light. We have to just kind of make up those numbers. Usually something that'll make the coding easier, but it's going to be moving. And once it's moving, when we want to stop it from moving, that has to go somewhere. Has to go into sliding, slowing down, has to be spread out over some sort of time interval. But these things are all very related. I might put some of these formulas on the quiz and ask for an explanation of what they are. So like I'll write the momentum formula there. P is mass times velocity, which, remember the words those letters are standing for. And then ask for a description of what that means. How it would apply in a game. I have a couple thoughts in my mind, and I'm not sure how to ask about the physics, but it is a course objective it is one of the objectives for this course. So what I decided to go with were the things that show up most often when debugging. As far as the calculation, the physics engine is going to handle those for us. We're in Godot, so we have a choice of physics engines. It's Bullet by default, which is one of the been one of the more popular physics engines for at least 25 years, probably longer. Been one of the most popular since the days of PlayStation 1. So I guess that was more like 95, so 30 years ago. So we have the physics engine is going to do the calculation, but when things start going wrong and we have to go back and debug them, we need to make sure we understand this, like friction pushing back. And you should have intuition, right? Even if you're making up new rules of physics, you have some intuition from the real world about what friction does and where it comes from and how these things interact. And I'm not going to try to trick you with the quiz. I decided to just write some formulas up there because we will code stuff occasionally, right? You might have to, sometimes you might have to code your actual code your momentum and then figure out where that changes, like what value is it, and then that becomes the this will be a good case. Your car that's stopping the car, the impulse was hit the brick wall. It's gonna be really, really loud versus hitting these shrubs. The sound effect is a car getting smashed. But because of momentum, this thing I was going to drive was going to lead back to this, and we'd see this formula in the middle somewhere. They all tie together when we start plugging one formula into another. But because of momentum, we know momentum is conserved, or energy. Energy is conserved. So one type of energy is sound energy. So when the car wrecks, whether it hits the wall or hits the bushes, it's going to make the same sound effect. But we can quickly calculate energy, and then that adjusts the volume of that sound effect. The same, really, really loud when we ran into the brick wall versus plug those same values into the energy thing here for running into the bushes. and we get a much softer sound effect and a little bit more realism in there. That might be one place where it would show up. Just had to introduce the formula somewhere, and it is not a. There's a lot to physics. 1, 2, 3, 4, 5. So I got 5 formulas circled on the board. Expect those to show up on the quiz. I'm still trying to think of how to put the quiz together for it. Because I'm not trying to trick y'all up and make the class impossible to pass. Trying to make it so we can program good games. These do show up when debugging games, and we try to get into the full realism, or when things go wrong, as opposed to we can track down the problem as opposed to randomly trying fixes until something randomly works. Studying physics is usually like 2 semesters minimum at a college. We don't need that much, but it's on our major learning objectives, and I'm not sure how much should be included. So a lot of it's built into the game engine. We'll see some of that on Wednesday, because we always have physics because we need the boundary between things. And in that boundary, there's going to be 2 forces applied, each going off in a different direction. Different materials and things will have an impact on whether they are completely equal or not. But we're always going to have 2 forces applied. We might need to adjust the equality of them. That's kind of what friction is, and how we get our negative acceleration to slowing down. We never want anything to happen instantaneously. So time interval is our frame rate at the best, maybe several frames. But we're going to think about things in like seconds or maybe minutes. We'll need to break it down to frame by frame for the game. If things start going wrong, we need to think about where the forces are applied, especially if we're in rigid bodies, because center of mass, the computer will estimate center of mass based on the shape of our model. So things might sometimes spin in a really weird direction. Bump into something and it starts spinning in like a weird direction. Maybe come back and figure out that. And the conserved quantities, the big thing there, so that you don't throw off players' intuition on how they should be controlling the game, is that nothing ever disappears. When something's moving, Newton's first law, it's going to keep moving until something stops it, but it doesn't disappear, which in coding, we're allowed to do. But when we do that in coding a video game, it's going to make things seem unrealistic, and the player is going to lose the predictability of when they need to push or let go of the controls, the buttons on the controller, to accurately play the game. So a very important thing. I'm working on what the quiz is. It won't be too difficult of a quiz as long as you remember these words, some of these words. Hopefully you took notes there, and what the formulas are going to be. Oh, matching one will probably be in there. Do a matching question. One side it'll say impulse, and on the other side it'll have all these four. Right? That question will probably be in there. That's the one that I think is most important, because to solve them, you just can grab that code, grab that, put it in the calculator, or write a little small side script with that formula, and then check stuff when you're debugging or whatever. But probably be a matching one, because a couple of those vocabulary terms, inertia. Let me read that on the board one more time. It's not up here. Inertia, which is Newton's first. Inertia is just that something stays in motion until it's acted upon, or vice versa. It doesn't move until something moves it. Right? This chair, is that on the camera? This chair is just going to stay here until something comes along and makes it move. And then it's going to keep moving until something comes along, in this case, the friction from the carpet, to make it stop. So inertia is an important one for prediction. Friction, That's how we get our negative acceleration. And this is built into the game engine, physics engine in the game engine, but usually too much. It takes too much to do that because we have to include it for everything. So we'll come back and just kind of hard code this just on the spots we want it. Then we might only need like 5 or 6 lines of code instead of adjusting every single property on every single object in the game. Impulse is just spread the forces out. Nothing happens instantaneously. And energy and momentum are conserved. Nothing goes away. It starts moving. When you stop it from moving, something else has to start moving in order to stop the first thing that was moving. A very quick introduction, just some formulas, not diving deep into physics, but if you're seriously interested in game development, you probably will want to take some physics classes somewhere in the future. Yeah. I wasn't sure what exactly the introduction to it should be. So I actually went through the last few, when I put that together, I went through the last few games and looked at what formulas I had to use in order to debug stuff without doing the random debugging. Without doing random changes until I figured out something that worked, actually figure out what the problem was and why game objects weren't moving and interacting correctly. We'll see that in a code example next time where we're actually going to use all of these things, and then hopefully it'll make a little bit more sense. But as far as the physics quiz, I'm going to write that later. And I'm not trying to trick you up with it, so hopefully it won't be too bad. Does anybody have any questions about that?
This is my weak spot.
It's kind of complicated. Yeah, really, physics is usually a 5 credit hour class. So it's usually like one of the longer science classes too, and there's a bunch of math leading into it. So be a little bit confusing. The way we're actually going to use it will hopefully make more sense when we see the code example on Wednesday. I'm going to wait till after class to go on Wednesday instead of talking to 4:50 today and then doing all lab day on Wednesday. So on Wednesday, you can do a little physics example, look at tile maps because you'll need that in your next project. And then we'll start doing stuff with groups. Group assignments start this week, so we'll probably do the breakout rooms on Zoom call, and then before we leave class, hopefully all the groups will have picked like communication methods, something simple, just the starting points. Right? Most people communicate through Discord this anymore, but are y'all gonna set up Zoom calls to work with, or Discord? Set up a Discord server, just email each other, or just randomly see what's going to happen. Let's get the first couple steps on the group project. We'll talk about that stuff on Thursday. I assume the silence means no questions. If you have any, let me know. Oh, yes.
So friction would affect acceleration, deceleration, right?
Yes. So think of friction as your deceleration, if you like those words. We call it the brake pedal in the car. But really, that's just a friction pad. It presses the brake pads up against the rotors or drums, causes a lot of friction, so then the tire can't spin as fast. If the tire can't spin as fast, momentum's carrying it forward, so then there's a lot of friction under the road. So you have an acceleration pedal and a friction pedal in your car. Think about that on your drive home. And then that's how you want to control your gains. And you'll usually hard code the friction in. So the force you're pushing forward, take some ratio of it. 80% is what slows you down. 60% of the force you're pushing, 60% of your forward acceleration is what slows you down. So as soon as this forward acceleration stops, then you have the acceleration slowing you down. The friction slowing you down. It takes a while to get used to. We'll see it in an example. That's basically what I just described there. That was what I just described for that quick pass was a preview of the example I have planned for Wednesday. Any other questions?
So we can hard code friction, like coefficient onto like tiles or objects, so that and then have like a ray pass detect it and then use that to affect,
Yeah, that's basically what we're gonna say on Wednesday.
oops.
You're right on track. We're getting there. I have a simplified version of that. But we'll see it then. And most game engines have it built in, so maybe we'll just look at the one built into the game engine, make it even easier. I'll see y'all Wednesday. Everybody have a great afternoon.
And all the levels is kind of like, this is what the frictions are.